Hey everybody, welcome back to our second video for Notes 2.2, where we are still looking at probability. So now that we've put another tool in our toolbox with the fundamental counting principle, we need to start looking at ways to calculate probabilities for very specific events. In our first lesson, we looked at probability in general, right? My number of options out of the total. However, there are situations that I'm dealing with events, multiple events, like flipping a coin and rolling a dice, where I have to go a little deeper. Two events. So I'm looking here at two events. Two events are considered independent if they have no impact on the other. For example, our dice and our coin. That has no impact. When I roll the dice, getting a 6 is completely separate, has no impact on flipping my coin and the results that I can get. Another example of independent would be the birth order or the birth gender of children, right? Having a little girl first did not change my options for my second child, right? I had Braylon, my daughter, first. I could have had a little girl second. It didn't change my options for the second kiddo. Independent. They have no impact. However, dependent events, I'm still looking at two separate events, two separate experiments. Dependent events are when one does impact the other. For example, maybe I eat, or maybe I select 2 pieces of candy, right? When I eat the first piece, it no longer exists. And so that changes my options for the second piece of candy. Or like earlier when we were doing our letters, that without replacement, when I did not replace my first letter, so looking here at B, when I did not replace my first letter, it changed my options for the second letter. If I cannot repeat, that makes me dependent. However, for A, when I could repeat, I had the same 26 options over and over and over again. One letter did not impact the other. So this would have been considered independent. This would be considered dependent. So let's have a couple of examples on that. Example 3. This is just asking, are we independent or are we dependent? A, 2 cards are selected from a standard deck without replacement. This would be considered dependent events. Because if you do not replace the first card, that changes the deck when you go to select a second card. Versus B, 1 card is selected from the standard deck, replaced, and then a second card is drawn. This scenario would make me independent for my events. Because you replace the first card, my deck stays the same. Kind of like our letters earlier, stayed the same when I go to select the second one. So if you have independent events, the multiplication rule for probability of independent events says, if I have 2 separate events going on, I can look at them individually and multiply them together. And tells me to multiply my two events. So, this should be example 4. It looks like this is example 3B, right? Choose 2 cards from a deck with replacement. What is the probability of choosing a king and then a spade? So these are 2 separate events. If I'm looking to choose a king and a spade, then I'm able to look at the probability of just a king, look at the probability of just a spade, and multiply them together. Because I'm replacing that card, these are just independent of each other, and I can look at them separately. So let's look again at our deck of cards from our last lesson. This is also something you're welcome to have on an exam. If I'm looking at the probability of a king, that would be the number of kings out of my total cards, just like we were doing in our last lesson. Well, there are 4 kings in the deck out of my total 52 cards. So the probability of a king was the 4 kings in the deck out of 52. Now I go back and I look at the probability of the spade, and I can do it just looking at spades. So here's my spades. So the number of spades goes on top. There are 13 of those still out of my total 52. Because these are independent, I was able to look at just the kings, just the spades, and then I'll be able to multiply those together. Now, how you do this is kind of up to you. You can either go ahead and multiply straight across because I'm multiplying fractions. 4 times 13 is 52. And 52 times 52 is 2,704. But if you do that, you still have to go back and reduce this. Notice I have a 52 in common. That would give me 1 out of 52. You can also do this in the calculator. If mine will turn on. You can do it as a fraction, or we could divide it in the calculator and give me 3 decimals. 0.019. The other thing you could have done, if you're comfortable with reducing your fractions ahead of time, remember cards often reduce. 4 out of 52 can reduce by dividing 4 out of both, giving me 1 out of 13. 13 and 52 can reduce by 13, giving me 1 out of 4. 1 times 1 is 1. 13 times 4 is 52. So either way, we get a result. The same result, I mean. If multiplying fractions and those kind of things are a struggle, please let me know. Most of what we do in this class is about what you're seeing right here. We don't get too crazy intense with our fractions, but we do have to mess with them some. Next example. Find the probability of choosing 2 face cards in a row. Assume the cards are chosen with replacement. Feel free to go ahead and pause this video and try this one, keeping in mind that when they say in a row, what they mean is I want to select a face card, FC, and then go back and select another face card, FC, replacing them in between. So I'm looking for the probability of a face card first and a face card again. So why don't you pause and try that? Assuming you have, remember if it's with replacement, that means we're independent. And we can look at these separate. The probability of a face card, again, tells me to multiply by the next probability of a face card. Completely separate events. So if I come back over here again to that deck of cards, if I'm looking for the probability of a face card, that's just the number of face cards out of my total. Friends, if you're not familiar with the deck, think face card, that's the ones with faces on it. There are 12 cards with a face out of 52. Now, because these are independent, that first probability, the 12 out of 52, will not change. Since I'm independent, when I go to do my next probability, I don't even have to think about it. Independent means that probability didn't change, and I am ready to multiply fractions. Looking at this, I go, man, I'm not really sure I can reduce, but I probably can. I know earlier I was able to divide a 4 out, so let's try that. 12 divided by 4 is 3. If you're not sure, 52 divided by 4, oh, yep, that works too, is 13. And I can't go any further. I'm going to multiply by, and I can reduce this one as well. 12 divided by 4 is 3. 52 divided by 4 is 13. If you want to pre-reduce, it will definitely help you in the long run. Now to multiply your fractions, 3 times 3 is 9. And 13 times 13 is 169. Because you have already reduced, you can actually stop right there. Or if your homework asks, you can get it into the decimal 0.053. The chances of getting 2 face cards in a row is 9 out of 169 options. So those are independent. If you have dependent, then we have to first talk about the fact that there are conditional probabilities. I tell you what, this video is going to run long if I don't stop here. So let me stop this video for independent. We're going to pick up on the next video right here at dependent.